In this example, we're going to work on an exponential decay type of problem. We're told, given the half-life of carbon-14 is 5,730 years, how long will it take for 1% of the original amount to remain? And we're going to assume this process follows an exponential decay model. So the first important thing is just to know the form for exponential decay. And that's going to look like this. Y of t equals CE to the negative KT. So here Y is whatever quantity we're interested in, and then T is going to be time. So for us, Y is going to be the amount of carbon-14 in whatever units, grams, whatever, it's not specified here, but the amount of carbon-14. And then T is going to be the time, we'll say in years. So one important thing here to notice about exponential decay is that this exponent is negative. That's the difference between exponential growth and exponential decay. Okay, so how do we proceed with this problem? So our ultimate goal is to determine how long it's going to take for 1% of the original amount to remain, the original amount of carbon-14. And the information we're given is just the half-life of carbon-14. So we can actually use this information about half-life to determine our rate constant K. And that's what's going to allow us to answer the question. So there are a few different ways we can go about this. Some of you might remember the formula for half-life. This would be the most convenient way. If you remember the formula, half-life is going to be the natural log of 2 over K. I'm told the half-life is 5,730 years, so in this way I can just directly solve for the rate constant K. So I would get K equals the natural log of 2 over 5,730. So that's one way to do it, and that's a very convenient way. But let's say that you forgot this half-life formula. Let's think about how we could approach this just from scratch. Okay, so the half-life means what it sounds like, that after 5,730 years, half of whatever quantity you started with is gone. So C here represents our initial amount of carbon-14. And we're not told what that is in the problem, but that doesn't matter. Okay, C just represents the initial amount. So then let's try to use that to solve for the half-life. So I'm going to set up an equation here. For Y, I'm going to plug in half of C. Okay, and by that I mean just half of whatever amount I started with. So half of C equals CE to the negative K T1 half. Right, so after T1 half, the half-life, I should be left with half of my initial amount. But I'm told what that half-life is, so I can go ahead and plug in that value. It was 5,730, so I have 1 half C equals CE to the negative 5,730 K. And now I'm just going to solve this relationship for K, and we'll see what we get. So if I divide both sides by C, I just get 1 half equals E to the negative 5,730 K. Then I can take the natural log of both sides to get rid of this exponent of E. So I get the natural log of 1 half equals negative 5,730 K, or I can write that as K equals the natural log of 1 half over negative 5,730. Well, that doesn't look quite the same as this, but it actually is, and let me tell you why. So the natural log of 1 half is actually a negative number. If you remember the properties of natural logs, this is a negative value. And I could actually rewrite that as the natural log of 2 to the negative 1 power. Okay, and then the properties of natural logs tell me that I can actually bring that -1 and make it a coefficient. So I end up with a negative natural log of 2 over negative 5730, and then we see the equivalence here, right? So I get ln2 over 5730. So either way you do this, whether you like to memorize formulas or whether you just like to understand the process and go about it that way, either way we come to the same value of k here. So let's plug that value of k into our formula. So now we have y of t equals ce to the negative natural log of 2 over 5730 t. So now what happens if I plug in some value of t? I am going to figure out the amount of carbon-14 that's left, and here it's in terms of C. So remember what my ultimate goal is. My ultimate goal is to figure out how long it'll take for 1% of the original amount to remain. So I'm looking to solve for some t value. So what I want to do is I want to plug in the appropriate y value, right? The appropriate amount of carbon-14. And in this case, I'm looking for the time when 1% of the original amount remains. So the way I can write that is just write it in terms of C and write 0.1 times C, or sorry, 1%. So 0.01 times C. So that's 1% of C equals CE to the negative ln2 over 5730 times t, and then I just solve for t in this equation. So I can cancel out a c on both sides. I get 0.01 equals e to the negative ln2 over 5730 times t. Take the natural log of both sides. That's going to get me the natural log of 0.01 equals negative natural log of 2 over 5730 times t. Right, when I took the natural log of both sides, it canceled out this e here. So natural log, natural log. So then in the end, I get t equals the natural log of 0.01 on top, and then on the bottom, this fraction, negative natural log of 2 over 5730. And if you evaluate that, get an approximate value, you're going to get about 38,069 years. And once again, that's how long it takes to decrease to 1% of the original amount of carbon-14.